everybody, my name is Tatiana and welcome to my video series on OTF Studio thin film software, a modern, smart and powerful software for designing, characterization, reverse engineering and monitoring of multi-layer optical coatings. Stress can cause a range of defects in optical coatings including buckling, cracking and delamination. In this video, I demonstrate how to minimize stress in multi-layer design using OTF Studio thin film software. This is the third video in the series on stress features. You will find the link to the previous video on the top of the screen. If we have a multi-layer design on a substrate consisting of two materials, high and low refractive indexes, we can calculate total thicknesses of each material. And if we know stresses in these materials, sigma H and sigma L, then we can create a merit function based on these stresses and based on total thicknesses and create corresponding target, which allows us to minimize the stress. It's important that these stresses should have opposite directions or opposite signs. So this is important. In this example, I will demonstrate the concept using a broadband anti-reflection coating designed to operate in the mid-infrared spectral range from 6 to 11 micron. Layer materials germanium and ytterbium fluoride, substrate zinc selenide, which is typical substrate for this spectral range. Estimated stresses in ytterbium fluoride 140 megapascal and assumed that estimated stress in germanium is minus 50 megapascal. I open my OTF Studio project that I used for the previous video for stress compensation. And here I have already loaded anti-reflection target from 6 to 11 micrometer, zinc selenide substrate, germanium and ytterbium fluoride materials. And now, additionally to anti-reflection spectral target, I create a new stress target. So I give a name, for example, stress mean, commit. And here, first of all, I choose a type of target. It will be custom. Target value will be 0 because I would like to minimize stress. Tolerances, for example, 1. And then I need to specify stresses sigma for germanium and ytterbium fluoride. Typically, stresses are known from experiments or from previous results, maybe from literature. But if it's not known, OTF Studio can estimate stresses based on your measurements. I assume that I know stress for ytterbium fluoride from experiments. This is 140. And for germanium, it's simply an example. Assume that I don't know, and then I can estimate stress using Stoney formula and profile measurements. So I need to fill these parameters in the panel, which opens. First of all, deflection of the uncoated substrate. For example, it will be 800 nanometer. Then deflection of the film of the substrate together with deposited thin film. It will be 500 nanometer. Substrate diameter is 2.5 centimeter and thickness is 1 millimeter, and thickness of the film will be, typically it's thick films, 1100 nanometer. And then 2 parameters of the substrate, 67.2 gigapascal Young modulus and 0.28 Poisson ratio. And then here we can see estimation for stresses in germanium. And we can take this value to the target, commit, and this value appears in the target, and we can see that both values have opposite signs. So it means that there is a chance to minimize the stress. So it makes sense only if stresses are opposite in opposite directions. So this is my stress target. I press commit. And load this target. And now I have 2 targets, spectral and stress, and we'll optimize with these targets. I load 1 layer as a starting design, 1 layer of germanium, focus on the design builder, choose gradual evolution and termination criteria. The maximum number of layers is 15. Run, and very fast we can see spectral performance, excellent spectral performance. For example, 15 layer coating. I can switch to auto and zoom in the plot. And we can see that the reflectance is really very low, but then check stresses. I can open values panel, place it to convenient location, and here merit function for stress, it's almost 0. It's 0.00018. So it's almost 0 stress. It means that stress is minimized in this design problem. So then let's discuss the structure. We can see in the design cross-section, we can see thick germanium layers and relatively thin ytterbium fluoride layers. If I focus on the total thickness, it will be 7.5 micron, and amount of germanium is 5.4, and for ytterbium fluoride is 2.1. This is because the absolute value of stress in germanium is 3 times lower than for ytterbium fluoride. So we expected approximately such a ratio of these 2 materials. This is one example of application of this powerful option, and the next video I will show more applications. Thank you for your watching. If you have questions, please contact me, and see you in the next video. Bye!